In my previous video, I showed the conversion of my CPU and computer to Logisim Evolution. This time, I'll show the usage of one of Evolution's capabilities to convert my CPU to VHDL. The reason to do this is that in order to put your design into a field-programmable gate array, or FPGA, you need to code it in a language such as VHDL or Verilog. Once it's in an FPGA, you can use your design in the real world, so to speak. Evolution will tell you if it can convert a given component to VHDL and Verilog. Note the green for convertible and red for not convertible. To use Evolution's conversion process, you should remove anything not convertible. My previous video showed my design using memory components in a jar library I created from the original Logisim to be used in Evolution. But those components are not convertible. So for the VHDL conversion, I had to use Evolution's memory components instead. I needed to put some of Evolution's memory components in subcircuits, since they take up way too much space. You can edit the circuit's appearance to make it look as close as possible to original Logisim's version of the component, making sure to put the ports in the same spots. Squares for inputs, circles for outputs. Note the diagram in the lower right-hand corner showing what the selected port indicator represents. If you want to get fancy, you can add text, lines, circles, etc. Since I use both rising and falling edge registers, I had to make a subcircuit for each type. I don't want to convert my whole computer design to VHDL, partly because most of the devices in the main circuit won't convert to VHDL. So I made a subcircuit called CPU0 with just the CPU and a few wires. This is what I'll run through the FPGA commander. You can choose the board you have. If yours is not listed, you can try to add it yourself. I'll select FPGA for you just for the heck of it. Clicking Annotate will add labels to any unlabeled components and subcircuits. Everything has to be called something. Download creates the code. Now the unmapped buttons and LEDs need to be mapped to the desired components on your board. Your options are highlighted in red. Select which one you want to assign. Look at any errors or warnings that pop up. This warning is a good one to heed. Since this particular line wasn't needed because I never did get that instruction to work, I never connected it to anything. I later discovered my VHDL design didn't work correctly because of that line, so I can either take it out here, replacing it with a constant 0 and rerunning the conversion, or I can fix it in the VHDL code. I think I'll fix it in the code later. I don't know how to deal with the gated clock warnings, so that could be a problem I would have to tackle in the actual FPGA implementation. By the way, there are some harmless remnants of the previous CPU design which I intentionally left in since I didn't know if I would later need them. Also, you can click on the red arrow icons to go right to the offending parts. While testing the VHDL program, I noticed the A register wasn't getting the right values. The design worked in Evolution, but not in VHDL. I figured out that if I put in a priority encoder to select the mux line, it would work. This seems stupid since it should work the same as selecting the mux line directly, but I guess there's something going on with gate delays or something. VHDL is based on Ada, and Ada is based on Pascal. So if you know either language, this will look a little familiar. It's not really practical to teach all of VHDL in this video, so I'll just cover some basics and things to look out for when using Evolution's generated VHDL code. The Entity section specifies the interface of the component. The architecture section, which is in the behavior files that Evolution generates, specifies the actual implementation of the component. You can have the entity and architecture sections in the same file if you want. Unfortunately, Evolution does have some bugs. For one, if you have a 32-bit ROM, it will incorrectly convert the ROM contents to VHDL. You can see the differences, and there is a pattern. On the left is the correct values I put in myself using a little program I wrote. I figured out what was wrong with Evolution. It has to do with triggering the signed bit of a 32-bit value in Java and then shifting that signed value. I fixed it and submitted the bug and my fix to the maintainers of Evolution. It will be in the next release. Or if you don't need all 32 bits, you could make your ROM 31 bits and avoid the bug. The next bug with Evolution probably also has to do with a 32-bit value being signed when it really shouldn't be. I use a 32-bit counter. Evolution sets max val to a -1 when it should be the maximum value a 32-bit unsigned integer value can have. But to avoid problems with signed values, I suggest changing it to the maximum value a signed integer 32-bit value can have. Now to fix something that isn't a bug in Evolution. The unconnected line I mentioned before. First, I have to find the right priority encoder. Then I have to change input 1 to a 0. The next thing might be a bug with Evolution, but I'm not sure. All of my priority encoders except this one are 4-input encoders. This 2-input encoder doesn't seem to work right. I suspected it is because since the others are 4-input, this one needs to be 4-input as well. So I'll make it a 4-input encoder, making the 2 additional lines 0. This address line needs to be 2 bits. However, I probably don't need to say it here, but it doesn't hurt. But I do definitely have to say it here. And I have to select only bit 0 of that line at the mux. Now to add in what I had to take out to make the conversion process work. Rather than edit it now in this video, I'll describe what had to be done. I had to add the divider component declaration to the ALU. Then I added the divider component instantiation to the ALU. Then I added 2 new signal lines for the output of the divider to go to the mux. Input line numbers 3 and 8. The values were 0 before. Then I created the divider entity and behavior files. I had to guess how to implement a divider, and I only implemented what my CPU design needed. Other CPU designs might need to more fully implement a divider. I also had to handle division by 0. I chose to do the same thing Evolution does in that case, setting the result to be the same as the dividend and the remainder to be 0. Since I'm not testing this on an actual FPGA 4U board, I don't need the top level and base VHDL code that Evolution creates. And I don't really need the CPU 0 code since that is somewhat redundant. But I do need to write a test bench to call the CPU component. The entity part has to be there but is empty in this case, since this will be the top level. So I declare the CPU and the program, which includes the memory. I declare the signals or wires needed. I instantiate the CPU and program components, pairing the parameters with the signal lines. And finally, I create a process to run the test. If the opcode is the data in instruction, I want to read from the keyboard. And if the CPU is ever in the halted state, I want to end the simulation early. Now the program and memory code. I create some aliases to reduce what has to be typed, and I specify a data type representing a memory bank. I need two banks, one for the program and one for the RAM. Unfortunately, for some reason, VHDL won't let me modify the contents of the memory representing the program and free space. So I need a different bank for the RAM. I copied the write line code from the standard VHDL libraries, but I omitted the line feed writing. This will allow me to write a character at a time to the display without a line feed after each character. Then I specify the procedures to write to the RAM and to the devices. In the case of the devices, it just outputs to the screen what would go to the devices. Then I create a process that loads the program from the file prog.raw and then does nothing. Then I call the write to device and RAM procedures in case a write is supposed to happen. Then if it's a read and not a write, I set the output of the memory to the appropriate value depending upon which memory bank should be accessed. I chose to use the free GHDL program to compile the code. If you have an FPGA board, most likely you'll have a VHDL IDE and compiler specific to that board. You would probably want to use that. Here's the batch file I created to compile it. The -A lines analyze the code, and the -E line elaborates the code. This is the Windows version of GHDL. If you have the Linux version, you can compile to an executable and even link in object files created from other languages. In that case, you could do things VHDL can't do. I commented out the components I previously mentioned I didn't need, the base and top level components as well as CPU 0. And here's the program I'll run with my CPU. Now I'll compile it. Here's the batch file I created to run it. The -R option runs it. Now I'll run it. Because of the way I coded the keyboard input, which is part of the test bench, not the CPU VHDL code, I have to type the desired option twice. You can see what would be sent to the devices. Now I'll use the free GTKWave program to display the waveform traces of any lines I desire. Here's the batch file I wrote to run it. You can select which lines you want to see. I'll now zoom out to see more of the range and look through all of the values as it ran the program. Well, it's great that it worked. From what I read, getting a design to be ready to be put in an FPGA involves a little more work. You have to deal with whatever gate delay timing issues or other timing constraints that might arise, as well as any peculiarities of the particular FPGA board and other design issues. You might need to use the specific software that came with your board to work those out. By the way, both Xilinx and Altera have free scaled-down versions of their software if you want to give those a try. My next Logisim video should be the Verilog version of this design. Spoiler alert, I got the Verilog version working as well. It seemed for a little bit that it wasn't going to work, but I got all the kinks worked out. Until next time, happy designing.